I'm a senior lecturer at Harper University, researching robotics and teaching robotics as well. So basically I love robots. So let's look at Harper. There it is. Okay, so it's founded in, I'll read it out because you might not be able to see it so well, founded in 1901, so it's a pretty old university. And we're on a 540 hectare estate. Now, we'll talk about hectares quite a lot in this talk, and I had to look up what a hectare is when I started at Harper 4 years ago. So it's 100 metres by 100 metres, okay? So it's 100 metres square is a hectare. And at the university, we teach crops, crop research, animals, food, land, and land management and engineering. Fairly small university, about 2,500 students. Compared to Stafford University, about 15,000 students. So on the big scheme of things, we're quite small. We're very specialised. We specialise in agriculture, but we're very applied. So we teach mechanical engineering, but we teach the theory, but we also teach the application as well. So you'll see some of this that we have. So yeah, we're doing a lot of research into robotics and agriculture. We're doing a lot of cutting-edge research in artificial intelligence, machine vision, and all of the latest technology, and we're basically applying it to help solve the food crisis that will be happening upon us. We're Modern University of the Year, #1, that was in 2017, and we have quite a lot of different accolades to our name, so we're very proud of our teaching and our student feedback. So this is a bird's eye view of Harper. I think one of the most interesting things we've got, which most unis don't have, is in the bottom right-hand corner we've got an off-road vehicle track. So students and staff like to take the 4x4s and give them a good razz around this off-road track, and that's good for stress relief, but it's also good fun for the students, and they work on their own vehicles as well and give them a good spin. The reason why I took the job at Harper University, I don't know if you can see it on here, but it's actually got an outdoor heated swimming pool. So that's open in the summer months, and we've also got on campus accommodation and big engineering blocks as well. So we're also a working farm. We sell our milk to Tesco's. We have about 400 cows. We have a beef unit as well, a pig unit. So you can just wander around the university and have a look at the sheep that have been born. They're just lambing at the moment. You can go and see the cows being milked. They get milked twice a day. You can actually go and milk the cows if you want to get up at 4 o'clock in the morning. We have a poultry unit, and we like to boast that we've got more chickens than students, and a sheep unit, and it's quite nice just to see the lambs, certainly in spring. That's an image of our rotation milking area, so that's our dairy. So the cows get onto this rotating platform, they get milked, and the cows actually spin. But it's not done by centrifugal acceleration, they spin very, very slowly. So they come off, it takes about 5 or 10 minutes, and then they've been fully milked. So it's quite a novel approach to milking. We've just installed robotic milkers in the university as well, and they're just being commissioned as we speak. And that's where the cows can go in when they feel like they need to be milked, and the robot goes, there's no humans involved, and it will milk the cows, and it makes it adds up the database and says, yeah, that cow's been milked, so we know what's happening with all the sheep and cows rather. Okay, so we've got a farm, 200 hectares of farm, grassland, 200 hectares, and we've got woodland and conservation areas as well. Well, let's focus in on engineering. So I've said that we do things like veterinary and land management and crop research. We've got the Dairy Crest building. We do a lot of research into food. We've got the Regional Food Academy and things like that. But we're also very proud of our agricultural epicentre, and we do a lot of research into the latest technologies in food and engineering. So we've got about 30 staff, 300 students. We do different courses, MEng courses, BEng courses, BSc, and MSc courses actually. MSc in Applied Mechatronic Engineering, which is the one that I hold. So we have students from all over the world, and they come to Harper to find out how to apply robotics in agriculture. So they come to learn the latest techniques in robotics. They study with myself, do the course, and then maybe go back to their own country and share the knowledge. So my office is actually in the Agricultural Engineering Innovation Centre. It was opened just a couple of years ago. And we house the National Centre for Precision Farming, So precision farming is a word that you'll hear quite a lot in this presentation. This is the latest buzzword in farming now. Precision farming and precision agriculture just means that we know the exact position of every seed that's been planted, we can recognise weeds automatically, and we're just making more efficient use of our farms. We can use image processing, we can use tractors which can follow straight tram lines, and just keep everything a bit neater. But it's not just about being neater, it's just about using the land more efficiently. So that's the precision farming. We also have tractor laboratories, lecture theatres, my office, mechatronics teaching room as well, and student offices. So let's have a look at a standard lecture room that we have in there. So the difference that you'll see, which is a bit different to other universities, besides the fact that we've got a tractor in the lecture room, is we have a huge door on the right-hand side as well. So we can bring vehicles in. So if we're talking about tractor electronics, we can drive a tractor in and show it. So we sort of practice what we preach. And this is just a bird's eye view of one of our mechatronics laboratories. You will see these tractors in videos soon. And the difference with these two green tractors, these two John Deere tractors, is they've got no seats and they've got no steering wheel. So they're completely controlled by a computer because we don't need anyone to sit on them and we don't need anyone to steer them. They're steered with a Google Map type interface and off they go and just driving by themselves. You'll see the one in the middle's got a huge bumper because safety is paramount with our systems, and big red buttons as well. So in case a robot tractor does come towards you when you're having a picnic, you know that it does actually have laser scanners, so it will detect you, but just in case there are bumpers on these things as well. But people do get a bit concerned about them. Okay, so that's just a bit of an overview of where I live most of the time during the week and where I work. Very dynamic environment. I'll tell you a bit more about our philosophy of farming with robots. So, why are we putting robots into farming? And probably the question that's on everyone's, or the answer maybe that's on everyone's lips is, aren't you just wanting to put people out of work? That's often a common answer to making robots. Is it just about getting rid of workers? Well, hopefully, with this presentation, I'll hope to dispel some of that. I mean, it's a knee-jerk reaction, and maybe it's maybe 1% true in some ways. But it's certainly, we don't really want to put people out of a job. We're trying to improve food security. So we're going to look at 4 items that we have with farming. So the top left-hand one, we've got crop establishment. So it's preparing the ground and planting the seed. And then we have phenotyping in the top right. So that's where we go along and we can look for the plants and see how well they're growing and if they need any kind of treatment or anything like that. And then the third one, bottom left, we've got more care, so we might have spraying or weeding, and then in the bottom right we've got harvesting. And I'll talk about selective harvesting, so you'll know what selective harvesting means at the end of this talk. So what we're doing is we're looking at a new system concept. So we're trying to improve food sustainability, lowering the cost of food production, and reducing the energy need in agriculture. So we're looking at a very sustainable system. We're trying to reduce the amount of waste in agriculture. We're trying to protect the environment as well, because robots aren't just stupid big machines that will just harvest everything. Robots are very intelligent. They can selectively harvest things. They can work like humans do, and that's our goal. And we want to make the production agriculture significantly more efficient. I mean, one of the big problems that we have, that the world has, is they say that by the 2050, the population will be 9 billion people. And it's less than half that now, so the big scare is, how on earth are we going to feed 9 billion people when there are countries like China who are demanding a different type of diet? They're demanding, quite rightly so, I suppose, a middle-class diet like we're used to. We're a very throwaway society, and we have a very high-protein diet, lots of meat and lots of vegetables and things like that. And these other countries, which are now gaining in money, want to eat better. So things aren't going to get easier. The land isn't, there's no more land. Really, we're building on land, we're building more houses. So we're not really putting land away for agriculture. So it's a big, big problem. And it's a problem that the entire world recognises. And a lot of the world is looking at Harper Adams in the UK, but there's also universities in Germany and all around the world who are working on these specific problems. And we all get together and do something about it. So we try and do our best to solve all these problems. So I'll give you one example. Okay, so knee-jerk reaction about spraying, robots doing spraying. Okay, so what happens when we are spraying a field? If the wind gets up, the person driving the vehicle just has to stop and go home. It's too windy to carry on spraying, so they might be able to continue the next day. But for example, if you have a robot spraying and the wind gets up and you've got a sensor on the robot, you can detect that it's started to get a bit windy, the robot could just stop and wait, and it could wait for 7 hours. The robot doesn't care, it's just a robot. It waits until the wind dies down, and then it can be programmed to start up again as soon as the wind's died down. And that might be 3 o'clock in the morning, and it's more efficiently, so it will get the job done. You just ask the robot to get the job done, and it will get the job done. So that's one little solution of why you might want to use robots to do some spraying, for example. Another big problem that we have in the UK is this soil compaction. So you might have noticed that tractors are getting bigger and bigger. You know, we started off with the ox and plough, and then we naturally progressed onto the vehicle, small tractors back in the 1950s, and now they're getting bigger and bigger. And the reason why they're getting bigger is because farmers want to cover the field faster, and they've got more horsepower, so they can drag more implements faster through the field. But the big problem is, as a tractor gets bigger, it's crushing the ground, it's ruining the substructure of the soil. So you've probably seen tram lines in fields now, which is a relatively new idea. You know, about 25 years ago, we didn't really have tram lines, but now there's tractors that are following specific lines. So yes, they're ruining the soil, but they're only ruining a small part of the soil. So one of the solutions is just to drive on specific parts of the land. But yes, soil compaction is a big problem. And the reason why farmers want to get around the field quicker, besides the fact that you can do more with it, is because of rain. We can't take our vehicle out when it's been raining, so when it's dry, we can take our vehicle out, and we've got to go around quickly and do our jobs before it starts to rain again. And if it has been raining, you put your tractor on, it's going to end up like this one here. So, one of the solutions that we've got for that is an ultralight seeding robot. So we have a small John Deere tractor, so you saw that in the lab, that was in the middle of the lab earlier on, in the earlier picture. And we've got some students on the left-hand side, so we do involve our students with all of these projects, and the students made this tractor into probably the most biggest and fun radio-controlled toy you'll ever play with. So it's a diesel-powered tractor, and they're just moving it around as if it's a radio-controlled car. So it's whizzing around in between the cones. It's front and rear wheels steer as well, and yeah, they're having a fair bit of fun with seeing that driving round. But now it has got a serious issue though, because if you zoom in on the ground of where that vehicle was, that's my flooded footprint. So the field that they were doing this in was in February, and we know that's quite a dismal wet month. And so standing on the grass, it's at field capacity. Now field capacity means that it's waterlogged basically. There's not water that you can see, but if you stand on the grass and pull your footprint up, it gets filled with water. So you've actually damaged some of the soil substructure there. But what you won't notice is the one that I've highlighted there, and that's the actual tyre track of that vehicle. So the tyre track has got less ground pressure than me walking on it. So how can that be? You know, I'm lighter than that John Deere tractor. But that John Deere tractor has got 4 wheels, and the tyre pressure is quite low, so it spreads out over a larger area. And you all remember that force and area are all interlinked, aren't they? Inversely proportional. So if you've got a small area, you've got a larger amount of force. So my footprint as a small area will damage the ground. Tractor, it's got 4 tyres, they're fairly wide and flat. We use low pressure tyres, so it doesn't damage the ground as much. So smaller, lighter seeding robots, and they can really seed the ground in any weather, even better than a person doing it. And although it's radio controlled at the minute, that's the first step that we do before we put computers in control. So the next step would be to put a computer on there, connect it to something like Google Earth, and then we can plot our route. And I'll show you the sort of route plot that we have. So we started a website called webfarming.com, and with web farming, it's not just an interactive Google Maps where you can highlight the outside of your field and say, I want to plough this field with a width of 1.2 meters, and it will automatically give you the tracks that the vehicle has to follow, which you might be able to see, they're just in yellow there, so that's the software does that. So it's not just that, but it also looks at which implements there are, and it's an entire inventory of vehicles and crops and a whole management system. So now we've taken the farmer into a position of a manager, where they want a job doing, they can see it from their Google images, and then they can just say where they want to be plotted, they can see what's available, and the robot tractor will get the implements. That's the idea. So far we've got the robot tractor to follow these types of tram lines, but obviously it can't automatically just choose the types of attachments that it needs. But there'll always be someone in control of the robots. So there will always be someone in the workshop who makes sure that they're filled up with fuel and will look after the vehicles. We're not trying to take people completely out of the equation. So we'll have a manager and we'll have someone on the shop floor. They might be looking over maybe 10 robots, but it's one person looking after 10 robots, and they'll be in control with the robots with an emergency stop switch if we need to. So that's our web farming, and that's our mapping system. So let's just talk about synchronized planting and what you can do with these small seeding robots. So you can have smaller robots, but you can have them working together. So you can see 2 robots here working together in synchronization. You can have 10 robots covering the field very quickly, very small, very light vehicles, and they're all working in a platoon. And we're actually doing a platooning project at the university now. And what you'll see there is where they've planted the seeds. Now they've used a very accurate punch planting method, and they've used GPS to find out exactly where they are. And our GPS is accurate to about 2.5 centimetres. So you only have to move 2.5 centimetres and it can pick up how much it changed. So it's very, very accurate. So yes, we can plant like that. And you might think, well, that's a bit boring. Who wants to see fields that look like that? You know, it's not very characterful, is it, really? But we're trying to improve farming here. And there is some advantages to all of this. One of the advantages is this. So you get these green things, and those green things are the crops that we want to eat. But you also get these red things. And the red things are weeds that start to grow. Now the difference is, the green things, we know exactly where they are. The red things are in places that we've not planted anything. So we could program a robot that knows where the plants are, and everything else must be a weed. Or you could just have a hoe. And if you have a hoe with the exact spacing of implements, you could do something like this. So you could, well, hoe in between and crossways like that. So you could build up hoeing, and you're doing interrow, and you're also doing intra-row as well. So you're weeding in between. So one of the problems is hoeing in one direction is okay, but it's very difficult to get hoeing in between those plants. So you can see that we have an organic solution. Hoeing is a nice organic, very old method of weed control. And that's one solution, by knowing exactly where we've planted things. So let's talk about weeds. Right, so we all like organic. You know, it's great to buy organic, and a lot of companies like GE's, growers, will always have an organic section. But organic is horrendously expensive. Yes, we all want to invest in organic, but it's difficult, and we don't really know the true story. So this is how organic farms are weeded. So there are people which hang on to the back of tractors like that, and they hang down, and they're manually pulling up all the weeds. So I'm not going to say whether that's a good job or not, because some people might like it, but that's how it's actually done. So with an organic farm, you can average about 300 weeds per metre square. So in a square metre, you can have about 300 weeds. If you sprayed it with herbicide, you get less than 50 weeds per hectare. And this is why it's so much cheaper currently to spray. I mean, just rough costs, and we'll talk about costs a bit later, to organically weed a hectare, it's about £1,000 for one pass, because you have to pay the people, and it takes quite a long time to do it. But you have to weed about 3 times in a season, so that's £3,000 per hectare to weed organically. If you're spraying, it costs about £50 per hectare, so the costs just don't quite add up yet, and of course there's a lot of person labour with the organics. So that's why we're looking at organic weeding, but using machines to do it. So we've been working with the University of Manchester, and we've been saying, okay, can we make machines and program them to be able to recognise plants and recognise weeds and find out what's going on? It's quite difficult for a machine to recognise the difference between a crop and a weed. but we've been looking at hyperspectral imaging. So hyperspectral imaging means you can light up the plant, but you don't light it up with just sunlight, you light it up with maybe infrared light, or maybe ultraviolet light, and this is in an enclosed box, and if you put ultraviolet light on certain things, you might have seen in different museums that they glow. So some things glow. Now everything glows, really, but different plants will glow in different ways. So this is a hyperspectral image of different types of plants, and it's just showing that they have a hyperspectral signature. So that might be one way, if we just look at how much they reflect, that we can recognize certain types of weeds from certain types of crops. So what we've built is a laser weeding system. So this goes on the back of a tractor, and it's a completely organic way of weeding. And what happens is, it's in a box, which is on the bottom right-hand side there, and it's attached to the back of a tractor, and it gets dragged along. Now inside that box, we have all of this stuff that you can see in that block diagram there. And what you have is a hyperspectral light, which is shining down on the crop. So that shines down on the crop, and then it reflects back into a camera. The camera goes into the computer makes some sort of, says, is it a weed or is it a crop? And then it makes a decision. It might make the decision to move a laser and to fire at the weed and blast it out of the soil. We're not really blasting it out of the soil, that would be very Star Wars, but what we're actually trying to do is minimize the amount of power we use in agriculture. So we just give it a little laser blast. Just a short, sharp, half a second, and what it does is it just burns the meristem, and the meristem is a growing point. So it recognizes the meristem, fires it at that, and then it stops it growing. So let's see this in action. So we're now looking from a GoPro camera, which is inside this weeding box, and what you've got is lettuce, and you've also got small weeds. You can't really see the weeds, but you might be able to see bits of smoke. So that's the laser which is moving, and it moves on a gimbal. So it can move around, and it can decide where it's going to fire at the weeds. So it moves around, and as it's driving along, that gimbal is actually tracking to allow the laser to dwell on a weed for about half a second, which it needs to just burn the meristem. So that's what you've got in the main video, and then at the top you've got how the computer recognizes things. So what you've got is those blue bits. So those blue bits you might have realized are the lettuce. So it recognizes those as lettuce. And then it's got a red bit around it. So that red bit is an exclusion zone, and that exclusion zone means that that is the bit that it's going to make sure that the laser is going to get. So it's because the weeds which are growing very close to the lettuce, that's the ones that it wants to aim for. The other ones can be taken out with a hoe or something like that, so they're quite easy to get rid of. But the ones that are very close to the crop are the ones that are very difficult to get out with a hoe. So that red bit is the bit where it decides, am I going to get this weed or not? So you can, can I rewind that? No? Anyway, so that's how it works. So you can just see that working. And it's all in an enclosed box, because it is a 50-watt laser. So it's a class 4, very dangerous. And yes, it's all in this enclosed environment. So another thing that we can do, which isn't quite organic, but we've got to just move with the times and be realistic with all of these things, is microspraying. If we can recognize the weeds automatically, we can make a robot go along and maybe just spray those weeds. So it's going along, those red bits are the weeds, and it's recognizing just the weeds, and it's just putting a small amount of pesticide or herbicide onto the weeds. Just a small microdot of herbicide. And that means that you're not spraying the whole field. That's so last century. We don't just spray everything now. We recognize where the weeds are. We just put a small dot onto the leaves itself. That goes down into the roots of the weed and just kills the weed. It doesn't leach into the watercourses, doesn't go onto the ground. It gets used by the weed itself. So that's work that we've also been doing. Okay, so I've just got a few figures for you, because I always find this quite interesting, working and talking to the people who actually grow our food. So 80% of our lettuce comes from G's growers. Okay, so they're based over in Cambridgeshire, so we get to work with them, and it's all grown in peat, in the peatland. It's very fertile ground, really. I don't know how long it's going to last. Every time I go there, another half a ton of it seems to have blown away. So I don't really know what the future is. But yes, they produce about 80% of the market, and there's just some of the figures that I mentioned. So pesticide, it says £20 per hectare, so maybe it is. But yes, mechanical hoeing is £1,000 per hectare, and that's just the things that we have to live with at the moment. Let's talk about something that we all love, strawberries. So, picking strawberries. We actually employ 90,000 people every summer to come and pick our strawberries and our soft fruits, because we won't do it. They try to employ British people, and we just won't do it. So we have to go overseas to Eastern Europe, and we bring them in by the busloads, and they are our soft fruit pickers. So our entire fruit market really relies on this seasonal labour. One of the big problems, actually, with our pound dropping, with Brexit, etc., is they can earn a lot more money by going to Germany. They can earn 20% more by going to Germany. So we have a bit of an issue here, and a lot of soft fruit growers are quite frightened about where they're going to get this seasonal labour from. Now, although that's a very bad thing, actually for us, it's a bit of a good thing, because one of the solutions is robotics. So we are actually looking at robotic strawberry pickers, and I'll show you a video of what we've been working on. But I'll just give you some figures. So yeah, 90,000 people we rely on for our soft fruit. If they don't come, we don't eat unless we go and pick it ourselves. So we produce 75,000 tonnes of strawberries each year, and 1 tonne is about 50,000 fruit. This is in the UK. And it costs about £860 per tonne, or 23 pence per punnet, if we're paying people to pick these things. The pickers earn about £7.20, £8.50 per hour, and we're looking at robotics. Okay, so robots can work about 16 hours, and then you've got a battery change. We don't want to work them 24 hours, really. But we've done the costs, and at the moment, with robotic technology, it would be 190% more expensive to get robots to do the job, because they are a lot slower and they're a lot more expensive. But with the current climate, the things I've just mentioned, it might start to even out a little bit and balance up. Now, one of the big problems we've got, and we have worked at this, is strawberry recognition. How do you recognize strawberry? Now, ripe strawberries are red, so you could program a computer to go for red things. That's not too bad, actually, so that you could do that. And you can see in the image here, the computer has picked out red strawberries. But the biggest problem we've got is occlusion. If you've got a red strawberry that's partially occluded by a green unripe strawberry, the computer can't work out that there's actually a ripe one if it goes behind. Building robots shows how intelligent humans are, because we would naturally do something like that. But to program a machine to do that, with our technology, we can't do it. And it's not just us who can't do it, it's not doable. So we are working on this kind of problem. We're looking at deep learning techniques and artificial intelligence, but it's not really doable at the moment. Yeah, we use 3D vision, we use cameras on arms as well, but it's a very difficult task. Now, something that the robot can do is it could also recognize green strawberries and put those into its database. And what it can do is, it says, right, I'm not going to pick that strawberry yet, I'm going to come back in 2 weeks' time and pick that strawberry. So it can put a marker, GPS marker, where was that unripe strawberry? Then it can come back and pick it. So no longer do we have to just pick everything and then just chuck out the unripe ones. We can take a record of where the unripe ones are and come back to them. And that's known as selective harvesting. So that's something that we will see in a lot of systems soon as well. Lettuce picking. If the lettuce isn't big enough, come back in 2 weeks' time. So let's have a look at our strawberry picking robot, which is heading off here. So the robot it's all self-contained. It's actually built on one of these disabled wheelchairs. So we bought one of those. We found an all-terrain disabled wheelchair. It's brilliant. We ripped the seat off it. I don't think the person who owned it was that happy, but and then we've got a computer to control it, and we've put a robot on top of it, robot arm, which is developed by HAU Robotics, who've also built robot arms for the NASA. And the computer recognises when the strawberry's in view, it stops the mobile robot, and then it starts picking. And when it's finished picking them, it then tells the mobile side to move along a bit, and it drives. And how it drives is it's got a laser scanner, so it can keep in a nice straight line. It goes between the punnets. So I don't know if you've been to a strawberry farm recently. I was quite surprised. They're not grown on the ground anymore. They're grown on tables. So they're on long tables with like legs on them. So they're at people's height. They're all in polytunnels. We've all seen the polytunnels, whether we love them or hate them. I think we all hate them really, but they do help us grow strawberries for longer. And it's good for robots because the laser scanner can pick up those legs and it can just see them as a straight line and then drive in between them. And then you'll see that it knows that there's no more strawberries left, and then it'll start moving on to the next set of strawberries as it drives along, which I think it did do just then. Yep, there we go. So off it goes, and then you've got the strawberries in line, and then it just sets off on the picking routine. There we go. And another thing to note is we don't handle the strawberry anymore. We program our robot to just pick the peduncle. So the peduncle is the bit that's growing, the green bit. So the computer can recognise a strawberry, it can work out where the peduncle is, and then we've got a little cutter that just takes the peduncle and cuts that strawberry. So we can then say this robot has been untouched by anything. So when you eat that strawberry, you're the first person to actually touch it. Okay, so selective harvesting. So as I mentioned, we work with lettuce growers. So this graphic, really, and this is just a bit of a concept diagram. Massey Ferguson did these concept diagrams for us a few years ago. And what we've got is a lettuce picking robot. We haven't built one yet, but it's the idea. And what you can see, though, is that it's left some lettuce behind. So in the bottom right, it's left them behind. So the robot has said, they're not ripe enough yet. I'm going to make a mark of where it is, GPS coordinate of where that lettuce is. I'm going to come back in a week's time and try again. So that's selective harvesting for you as well. So it's just making more efficient use of the field rather than just harvesting the whole lot and then throwing away about 40% of it, which is what can happen in situations. So let's have a look at our autonomous driving tractor. So we've got a lot of technology on this tractor. One of the good things, really, about putting technology into farming is it's a worldwide problem that people aren't going into farming these days. And the reason why is because it's not exciting for the young people. In Japan, the average age of the farmer is 65 years old. So they've got to, do all these manual tasks. They're getting too old for it. And in the UK, the average age is a little bit younger, but it's not much younger. If we can put technology back into farming, it can attract young people to develop and to be involved in agriculture because, robots, well, I think robots are exciting, so maybe it'll excite people to be back into this environment. So we've got a whole lot of stuff here. GPS, RTK GPS means it's 2.5 centimetres accurate. LiDAR is a laser scanner. Collapsible bumper, Wi-Fi, they're all Wi-Fi enabled. And they've all got computers built into them, lots of computers built into them. So let's have a look at one in action. So this is actually filmed by drone. So we have drones at the university, and we use them for spraying research, we use them for filming as well. So this is part of the field, around the back of my office actually. And what we'll do is we'll just spin around and we'll see an autonomous tractor. It's driving quite near the car park, so we do trust these things. And there it is. Now what I like about this video is you can see where it's been before. You can see that it's got a nice straight track to it. And it's been programmed to go over this track several times, just to prove if it really works. And it's done a headland turn, and off it goes. Fairly slow and steady, but it works. And you can see the film crew there as well, and it's completely autonomous. So we've just told it waypoints, and off it goes. Now that's all right if you've got a tractor which is just going in a nice flat field, but we know that fields, certainly fields in the UK, aren't nice flat fields, and sometimes there's obstacles. So some of my work is this. So I've got a laser scanner on the front of the tractor, and it's controlling the steering of the tractor. So it's turning to avoid the fence. So we might have programmed it to go into the field, but there's actually a fence in the way. We don't know the exact location of all the fence poles, so there's a laser scanner which can pick up a fence post, and then say, okay, I'm going to turn the tractor to avoid that fence panel. So it's steering around that. So it's a bit of autonomy there. Now, one of our biggest things at the moment is the hands-free hectare. So we just finished this last year's growing season, and we basically worked on this project in about a year. And it's a world first. So it's the world's first hectare which is completely farmed by robot. So no human being has been in this field since we started this project. So the ground has been prepared by robot, it's been sprayed, it's been seeded by robot, they've taken samples of the soil, and to do that they have to send drones in there with little grabbers. The drones landed, a bit like something you find on Mars, grab a piece of soil sample and bring it back to the agronomist, That's a word that I didn't know before I started at Harper Adams, but an agronomist is someone who takes samples from the field and says, you know, what's the soil quality like? Does it need an addition of a fertilizer or so? So that's agronomy for you. So yeah, so we've got this, and you can see it autonomously spraying. And you can see videos of this on our website. I can't fast forward at the minute, but yeah, we've got the whole thing. So we had an autonomous combine harvester as well, and that was quite impressive because when you're combining, you're taking up the wheat, and then the combine can hold a certain amount of wheat, but you have a tractor running alongside it. So what we did was we had a robot combine harvester and a robot tractor, and they were following each other, and then the combine harvester was putting all the wheat, chaff, whatever, into this tractor. So quite impressive. So with drones, we're looking at spraying with drones. So the idea of spraying with a drone is you're not going to compact the ground. So you don't have to drive over the ground to spray it, you can do it from the air. Now current UK legislation says that we can't spray from the air. We're not Australia, so we're not allowed to do it. But we have research facilities, we've got enclosed fields, for example, an indoor field where we can test out these things. So this drone can hold about 20 kilos of spray, and it can run for about 25 minutes. And it can spray quite a lot in that time. And we're doing research to say, well, if we spray from a drone, is it going to drift? Is it going to drift into where it shouldn't go? Because one of the problems is you've got 4 propellers and you've got a downdraft. So we're looking at different spray nozzles which will ensure that the spray goes in the right direction. So that's some of the research that we're big on at the moment. So, and we are advising Parliament on this. So the people at Harper Adams do go down to Parliament. We say what's happening, and we say, come on, you know, we've got to move with the times a little bit. We've got to change some of the legislations, and this is a proof to show that it is a safe thing to do. So that's what we're working on. So we're working with part of the National Centre for Precision Farming, the Civil Aviation Authority, we're quite friendly with them, the Chemical Regulation Directorate, and many drone companies as well. So we're trying to accredit drones to use spray. Okay, so that's a lot of our research, but what about teaching? So we do teach, you know, we teach mechanical engineering, we teach engineering degrees, but everything tends to have a bit of an agricultural application. Not to say that you have to be a farmer when you graduate, you can go and do what you like, but you do have a bit of practical knowledge from that. I also run a summer school, so I have 16 students from Northwest Academy in China, and I've got another group from the UK actually coming at the end of this month. And they all get to use these small robot cars. So they're little they were radio-controlled cars, but I've put a computer on them. And I've built 10 of these, and I'm just building another 10 at the moment as well. They've got a microcontroller on, which means a computer you can program, GPS, compass, display, and basically I teach students to program by using these vehicles, and they take them out into a field. And these vehicles can do exactly the same thing that the robot tractors can do. They can drive by themselves, they know if they've tilted over because they've got tilt sensors on, they've all got communication, so if one's tilted over it could ping to its other ones and say, I've tilted over, my location is blah, 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 come and rescue me. So you can do all sorts of quite clever things with these vehicles, but they're only about that big. So the students can have them on the desktop because computer power with small microcontrollers is powerful enough really to be able to do navigation and behaviours and to really, you know, do the high power things that only PCs could do previously. So we've got some pretty happy students there. So that traffic cone they had to program a robot to get to the GPS coordinates of that cone, which was probably about 100 meters away. So they're quite happy because it wobbled its way through the field and stopped at the right place. So yeah, some more images of students happily. It's a nice summer school because the weather's always good, touch wood, and gets you out inside programming, outside applying it. And yeah, nice group of students there. We also are involved in the international competition of the Field Robot event, which you might not have heard of, but the Field Robot event is roboticists who work in agriculture, and there are quite a lot around the world, believe it or not, and this is a competition that happens every year, and we always enter it, and we usually get into a good position. Sometimes we don't always win it, but sometimes we do. We're going to Germany in June to take our robot along, and basically these robots are autonomous vehicles which can navigate between rows of maize. And then when they're at the end of the field, they turn around and go down the next row, and they might find weeds, and they might spray the weeds, but they basically do autonomous tasks. Now, we hosted it last year, so that was great fun. We had people from as far as Mexico who'd come over, and we spent a few days playing with robots, and we found some really good teams. I was blown away by one team, actually, who came, and they'd even brought their own 3D printer along from Germany. And they were a school as well. So they brought a 3D printer just in case part of the robot broke, they could just print another one. So there you know, I'm amazed, you know, it'll never stop amazing me what people are coming up with these days. So yes, the robots use image processing, they're completely autonomous, and they've got different tasks to do. Okay, so that's just an image of some of the robots, not that we've made, but that are around Europe. There is quite a move to make these autonomous robots. For example, Sydney, Australia, they're very big on these types of robots as well, autonomous robots. But you know, this is the good, the bad and the ugly of the lineup of the robots, which I quite like to show. So, precision farming, it really means smart farming. It's using technology and being clever about what we do. Let's not just scatter seeds and hope that they grow, but let's know where every single seed has been planted, let's take care for every single seed, and if that seed's not growing properly, let's stick a seed in that position that it is growing. Let's not harvest an entire field in the hope that we're going to get food out of it. Let's just harvest what we need, and if something isn't edible, let's come back for it, or use that space to grow something else. So I'm quite heartened about using robots and intelligence to be smarter, to help solve this food crisis. We also want to minimise the energy going into crop production. So you saw that we can use a laser to kill a weed, and we're not trying to be Star Wars here, we're just trying to use the smallest amount of energy. When we spray, we don't want to spray the entire field, we just want to put a micro droplet on. So we can save 99.9% of chemicals by doing that, or even 100% if we're using lasers. So we want to be making smaller, smarter, lighter machines, which means less soil damage and bigger trafficability window. That means that you've got more time to work in your fields in between the rain because these vehicles are smaller and lighter. They're not going to do the sort of damage that you saw at the start, where that tractor was completely bogged down and it wouldn't get out anywhere. These vehicles, these robots are going to be a lot smaller and smarter. So, you know, can it help with climate change, for example? So, we believe the future of precision farming, so it's based on a new mechanisation system with small, smart, light machines. And there it is. Oh, this is another concept, but I do like that picture anyway. So you've got the tracked robot with CPUs, computers on, and all sorts of gubbins which are working in the field. So that's it. Thank you very much. Thanks very much for listening.